Hi, this is the second part of the first lesson. Here we will focus on strong inversion, and for this and in this section we will see the derivation of the voltage current equation. For strong inversion, we will see the operation regions in this strong inversion. We will observe second order effects and finally the small signal model. As we saw in the previous session, when we inject a gate voltage in the CMOS transistor greater than the threshold, we will generate a free electric charge. For the moment, let's assume that the source and the drain are connected to ground. So we know the current in any semiconductor is equal to the charge per density times the velocity of the charge. And now if we in our CMOS transistor we can calculate the charge per unit of longitude, and this will be the width of our transistor times the capacitance of the oxide per unit area here, and this times the voltage between gate and source minus VTH. Well, here from here we will choose a model of a transistor based on the source. So that means that the bulk will be always connected to ground to analyze the simplified model, and we will reference everything with the source. Well, from the previous equation, we have the relationship of the charge per density, but now let's vary the drain source voltage. We will inject a voltage VD in the drain, and well, the source will keep on ground. Remember that the bulk is connected to ground here. And now in our first equation that the current is equal to the charge per the velocity, we can replace the charge for this amount, and then we can replace also the velocity. Now the velocity will be the mobility. In this case we are analyzing for an CMOS transistors, then this will be the mobility of the electrons, and times the gradient at a certain point in our transistor, which is this is the gradient of the voltage with respect to the dx. Okay. If we integrate this equation, let's integrate from 0 to IL, sorry, 0 to L, and then here also we integrate from 0 to BDS. No, this dx moves here, and then well, we have here a bgx, so we will have a quadratic function. No? Well, the result of this integration is this equation. It will be our first equation. And now let's plot this equation. So we have here a quadratic function, so it's a parabolic, but with a minus sign. So this will give us a maximum value in a parabolic. Well, what is this value? We can derive this equation. We can derive ID over PDS. If you do that, then you will obtain that the voltage at that point is equal to BGS minus VTH. Okay, well, here is we have this point for a fixed value of BGS. So this equation triode region will be valid until those points, and from there, well, we will see later that it tends to be constant, the current. Well, the mobility times the capacitance of the oxide is usually provided for from the fabricant, and we design our circuits changing the aspect ratio of the transistor, and also depending on the bias voltage, no? Gate source, we can vary gate source voltage, and we will call VGS minus VTH the overdrive voltage. Also, the VTH voltage depends on the fabrication process. No, it's not a physics uh, component, but it's more a mathematical assumption that we use. Well, now we will move to a subregion, a linear region. This is just a special case of the triode region. So here, if the drain source voltage is very small, we can neglect this term and we can simplify the current as a relationship only with this term, the first term. So how small? Well, let's say that BDS is much smaller than 2 times BGS minus BTH. If we use that, we obtain the equation number 4. And if you see here, we have BDS here, the current that flows through those terminals, and a constant in between. So this is similar to the resistance relationship. In the resistance, we have a linear relationship within the current and the voltage. If we pass the ID to the second part of the equation, we can obtain the resistance of this transistor. Okay. Well, so this value is only valid when we are we are in triode region, but values of BDS are small. So we can control the resistance of this module by providing different gate source voltage. So we have a control resistance device. Well, now let's move to the saturation region. So far we have seen that until VGS minus VTH we reach the maximum current from previous equation, but from here what it happens is that our transistor will try to keep the same amount of current, so it will be almost constant from this point. Now in this point, when VDS is equal to VGS minus VTH, it refers to this graphic here, and what it happens at this point is that the gradient of charge exactly finish at the end of the channel length. So at this point L here. So at this point, when it finishes, the gradient of electrons is called pinch off. But now what happens if we, from this point, we still increase the drain source voltage? If we increase the drain source voltage, then this pinch off point will finish earlier, as you see in the second graphic. So here is finishing earlier, and this variation of the length delta L, it should be proportional to the voltage that we increase between BDS. So this BDS, well, not exactly DL, but delta DL over L. Well, there are some second order effects because we have only used very simplified models. One of the first second order effects is called body effect. So we analyzed this effect in the previous video, and now we repeat that part. First, when we have the source and the bulk connected to the ground terminal, we have certain depletion region generated close to the source and an amount of free electrons also. But if we now increase the voltage in the source with respect to the bulk, what we will have is that in the source we increase the reverse bias with respect to the bulk, so our depletion region now is greater than the previous version here, and this will reduce the amount of free electrons that we have close to the source. If we want to keep the same amount of electrons here, what we will have to do is that we have to increase the BGS voltage. So now we need more voltage to have free electrons. Mathematically, the relationship between the threshold voltage is given by this. Now the threshold voltage will be equal to initial threshold voltage when the source bulk is equal to 0 plus a function that depends on the square root of the voltage between the source and the bulk. So as you can see here, it means that our threshold voltage will be greater when we increase the source voltage. Another second effect is the channel length modulation. As we saw in the previous slide, when the BDS voltage is greater than BGS minus BTH, sorry, this is greater, then the pinch-off finish earlier than L, and this relationship is almost linear. If we replace those equations in our first equation, ID times 1 over 2 mobility COX W over L BGS minus BTH, well, let's say this one. But now our length is equal to L minus delta L. We can replace this equation here, and also delta L over L equal to lambda BDS, a linear relationship. We will end up with equation number 5. And this tells us that we will have an increase in the current, a linear increase as a function of BDS. And then, so we have here a slope. Okay. Well, in strong inversion, we said that the BGS should be greater than BTH, and for voltage less than BTH, we said that the current is 0, but this is not exactly true. What in fact happens is that we still generate charge and surface potential for values smaller than BTH, and if we, instead of having a linear scale, we plot as a logarithmic scale, we will observe that they have a weak inversion in the weak inversion region and exponential relationship. Okay, so this equation, the approximate current in this region is given by this expression, for expression number 7. And here the exponential is to the power of BGAs over kappa times the thermal potential. Thermal potential around 26 millivolts, and kappa depends on the fabrication conditions of our device. Well, also here you can see that the threshold voltage is between weak and strong inversion. So we will say that this quadratic expression does not start from VTH, no? So a little bit greater than VTH. Well, now we will move to the small signal model, and for this I will start with the transconductance. The transconductance of the transition can be defined, or is defined, as the derivation of the current with respect to the BGAs. So if we have our equation of the current in the as half mu Cox times W over L BGS minus PTH, this to the squared power. If now we derive this equation as a function of BGS, then this goes down with this, and we will get equation number 8. And now, well, we can also use this equation number 8 with our initial equation, replace BGS minus BTH, and we will get a similar equation, but now as a function of the current. Similarly, we can use this equation, equation number 8, and our new equation, where we can elevate this to the power 2, this also to the power 2, and we will get then the transconductance, another equation for the transconductance that has a relationship with ID and BGS. Well, now let's plot those equations. Equation number 8, when we increase BGS, the transconductance will also increase, no? Provided that W over L is constant. We have this equation. Well, you can see that here this relationship is linear. Now in the second equation, we can provide W over L constant, and this will depend from it will have a relationship of square root of ID. If we plot the square root of ID relations, then we will have this waveform. And then the last equation here, if we give a constant ID, if we increase BGS, our transconductance will decrease. Well, in addition to construct our small signal, we also need the output resistance between those two terminals, BD and BS. And this we can give from our previous equation of the current 1 over 2 times mu mobility Cox W over L BGS minus BTH to the power of 2, but now times 1 plus lambda BDS. Okay, so the small in a small signal, the resistance here will be giving us the voltage over the current, no? But now will be the derivative of the voltage with respect to the current. So if we derive this relationship delta BDS. Here also, here we have a linear relationship, so this can goes away. We have lambda, and this term here, no? Mu 1 over 2 mu Cox with WL. As we saw before, we can approximate this one to the current ID. And then we can inverse each part of the equation, and the resistance will be equal to 1 over lambda ID. Well, this is the reference that I am using, and thank you very much for your attention.